recording. Okay, so now we will do now a single bit addition. We will do now a single bit addition. What is the single bit addition? What is our objective? First, we need to define the problem. So let's assume we want to add two numbers. We want to add two numbers, and it can be any numbers. For instance, we want to add this number x and y. We want to add x and y, and let's assume the number of bits are 4, x3, x2, x1, and x0, and then y3, y2, y1, and y0. Which one is the most significant bit? And y3. What is the most least significant bits? x0. Okay, now when we add each individual bits, we get some results. Let's assume I call this as s0, s1, s2, and s3, which is actually the sum. So this is the sum 0, sum 1, sum 2, and sum 3. But now if you look at each individual bits, let's assume if x0 is 1 and y0 is 1, 1 is what? 0, and then there is a carry. Okay, so now we have some C0, C1, C2, and C3. So actually this C0 is the carry out from this stage. And then if you look at here, so we can also have this carry in initially, which is 0. And then when we have a carry out from this stage, it will become what? Carry in from this. So now this one is, we call this as carry in, and this one is what? Sum digits, and this one is called as carry out. And the carry out from this stage will become the carry in for the next stage. So now if you look at here, this is C0. I call it C in 0. C in 0 is actually 0 because it's adding. And now what is C in 1? C0. So the carry from this stage, carry out from this stage will become the carry in for the next stage. Similarly, if you look at here, C in 2, what is C in 2? C1. And then what about here? C in 3 is what? C2. So this carry. So now if you look at this problem, so we look at this problem, so we want to perform an addition of two individual bits. We want to perform an addition of two individual bits. How do we call these bits? X and y, and carry in and carry out. Okay, so now, so we can we see here, so okay, now we have a 1-bit addition. We have a 1-bit addition. We want to perform an addition of a 1 bit. What are the inputs? What are the inputs? Please think, 1-bit addition. What are the inputs to this addition, 1-bit addition? Talking journal. Xi. And then what is the other inputs? Yi. What is now the other input? Cin. And what is the output? Yes, please. Si. Okay, and what is the other output? Cout. Okay, we can call it as Cout, COI, and then we can say Cin I. Got it? Okay, now what is the range of I? What is the range of I? So I belongs to a set. So I can belong to a set of 0, 1, 2, and 3. Why? How many bits are there? 4 bits. So we can say I in general, if you are talk to term, so I may belong to this subset of what? 0, 1, 2 until what? N minus 1. You got it? Okay, so now what is our objective? What is our objective in this class? Our objective is to perform a single bit addition. Any question? Proceed. Okay, now we have two inputs, So we have x and y. We call this as xi, yi, and cni minus 1. And what is, okay, can if you look at here, so what is COI? Please look at here. CO, this is carry out. COI is what? C in what? I minus 1. Because what is C in 0 is actually 0. And C in 1 is actually C out 0. Got it? Any question? So COI, this is called as the carry out to the next stage is equal to the carry in to the, sorry, we can say carry in of stage I is equal to carry out of stage I plus. Got it? Any question? Should we proceed? I'll explain this with an example. Okay. Now, should I rub this off? Should I rub this off? You may take a screenshot and then I can write something. And then I will explain how it works. And I'm also recording this. You can also see the recording. Okay, please refer to the, so you know the yes, please. Yes, I'm recording this. Okay, so I'm then rubbing this off. Now, if you look at here, now we have two different things. So now we have an adder. So we have the input x and y. These are the individual bits. And now this is carry in. What is carry in? How do they call it? Z. I call it again. So you can have different names. Doesn't matter. And now we have this. Now we have then C, and now we have this S. So how many possible combination are there? How many possible combination are there for X, Y, Z? So the possible combination can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. These are the 8 different possible combination. So when we add all of these 0, what is, both are 0, 0? Then 1, sum is 1, carry 0. Single 1, sum is 1, carry 0. Okay, 1, 1. Sum is 0, carries 1. 1. Sum is 1, carries 0. Single 1. 2 ones. 0, 1. 2 ones. And then 3 ones. Both are 1. So now this is called as the description of a single bit addition. So, okay. So now there are 8 possible combination. Now I have put it in the form of a table. So now we have this table. So now there are 4 possible combination. 0, 0, 0, 0, 0, 1, 0, 1, the second row, the third row, the fourth row. Got it? Then when we have carry of 1, 1, 0, 0 is 0, 1, 1, 0, 1 is 1, 0, 1, 1, 0 is 1, 0, 1, 1, 1 is 1, 1. The same table. Got it? Any question? So far clear? Yes, please. Z is carry in. This is carry in. This is carry out. The same thing. So Z is carry in and C is what? Carry out. So now you use different, whenever you're writing a C++ program, so you can say int AB. You're defining 2 variables with A and B. He's saying int XY. He's defining the same variable with a different name, X and Y. So these are just different name and different terminologies. Yes, please.
So why do we need Z? Why do we need carry in if we're just adding X and Y?
Which one?
If you're adding X and Y, why do we need carry in?
Because, okay, now when we want to perform a multi-bit addition, I will come in the next slide. Okay, I will explain this in the next slide. Why do we require? Okay, now this is an example. So now if you look at here, what is n here? We want to add 2 numbers, 1, 2, 3, 4, 5. How many bits? 5. How many bits? 5. Okay, now I'll explain this with an example. If we want to do this addition, so now we want to add the least significant bit. We want to add what? 1 and 1. When we add 1, the sum is what? 0. Carry is what? 1. Then we move this. This is carry in. This is carry in, which is actually what? Z. And this is carry out, the red one, which is what? C. Got it? Okay, now we want to perform this addition. Then this carry out from this stage will become the carry in for the next stage. So what is this? Yes, please. What is this? 1 Z. And what is this? X. What is this? Y. What is this? S. What is this? C. Got it? Yes, please.
So, if the carry in, how do you already know what it is before you add it? Like, because you already know it, 0, 0, 1.
No, so basically we are adding two numbers. We are adding two numbers. So now if we are adding two numbers, so there, okay, I will explain this with an example. I want to add simple 5, 3 and 9, 8. What is carry in 0? 0 or 1? 0. What is 8, 3? 11. 1 is 1, 1 is here. Now this is the carry. So for the least significant digit, carry is 0 always.
Yeah, but then you wrote the carry in for all of them. How did you know? Because you wrote 0, 1, 0, 1 before you did the addition.
Which one?
You said Z is the carry in?
Yes.
So you wrote all of them before
You know, these are all of the possible combinations. So if we say, okay, please, okay, I will explain it. So you say why this is 0 or this is 1?
No. I'm saying how do you already know the carry in before you did the addition?
Which carry in? What about carry in?
You said the Z is carry in?
This Z is carry in. Okay, now, okay, I will explain. This Z is carry in for this bit. This is the carry in for this stage. This is the carry in for this stage. This is the carry out from the previous stage, and this is the carry in for the next stage.
Okay, so you're not doing addition, you're just showing us all the possible.
We are showing all of the possible combination, because if let's assume if we say X, Y and Z, it's one bit, and it's one bit. How many bits are there? 3 bits. How many possible combination? 8. So we can have 8 different possible combination, and this is the table for all of these possible combination. Now you got it? So okay, so now we can have, okay, the first example, it can be 0, 0, 0. Yes, please. This stage, it can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So it can be all of the possible combination that we can have. Yes, please. So should we, okay, now, so now if what we are adding 1 and 1, the carry in was 0, the sum is 0, and C out is 1. It will become the carry in for the next stage. So now 1, 1 and 1 is what? 1, and this will become what? Carry in for the next stage. So now it is 0, 0 and becomes 1. Got it? And then we perform this addition, and now this is the carry out, okay, and this one is carry in. So can you see this? What is this? This is actually Z. What is this? Xi. What is this? Yi. And what is this? Si. And this is what? C out. C out. Got it? So now this is the carry out, and this is the carry in. Yes, please.
So we had the 1, 1, we have x is 0 and
Which one? Win?
x is 0 and the carry in is 1.
Yeah.
So 1, 1 will become 0 again.
Yeah. 1 will become 0 again. Okay. Now it's also very simple. So okay. Say so now think from other perspective, from other angle. So you say 1 plus 1, 2 plus 1, 3, 1, 1. 1 plus 1, 2, code is 1, 0. 1 plus 1, 2, code is 1, 0. Got it? Think from different angles. Got it? So you can also calculate it like this. 0, 0, 0 is all 0. Carry 0, both are 0. Okay. Now when we want to perform subtractions, so two numbers can be subtracting each for pair of digits together with borrowing from them. The same thing, you do it in decimal. 7 minus 7 is 0. 2 minus 3. You need to borrow 1. It will become what? 12. 12 minus 3 is 9. It becomes 5. 5 minus 5 is 0. Now let's do it here. How do we solve it? Okay. I'm rubbing this off. Okay. Now 1, 1, 0, 1, 1, and then 1, 0, 0, 1, 1. 1 minus 1, 0. So it's 0 1. No problem. 1 1. Okay. 0 1. 1 minus 1 0. What do we need to do? Borrow. We need to borrow, but it doesn't have the money. We need to borrow from here. So now it's 1. We borrow from here. It become 1 0. 1 0 is actually 2. But it gives 1 to it. It become what? 1 0, which is 2. So when it borrows here, so 2 minus 1 is what? 1. It will become 1. So actually 2 minus 1 is 1. Okay, now it is now 1, not 2, because it has given borrow. So 1 minus 0 is 1. 1 0 is 1. 1 minus 1 0. Okay, now if you look at the binary for this, okay, 1 2 4 8 16. 16 plus 8 24 plus 1 25. 25. Okay, now we are subtracting. 16 plus 3 what? 19. What is the result? 6. Oh, now it becomes 0. Yes, it's 0. And now it's equivalent to 6. Got it? So the same thing that how do you, so now this is the same, in the same way you do the subtraction in your decimal format, then you do the subtraction in binary format. Okay, now if you look at here, the binary multiplication. So when we want to multiply two numbers, the first one is the multiplicand, which is shown in red. The second one is the multiplier, which is shown in blue. And now we get different partial products. Okay, now I'm talking in general terms. So should I rub this off? I'm rubbing this off, and then okay. So now given, okay, now there is one formula, and then before explaining this, let's assume if we want to add two n-bit numbers. If we want to add two n-bit numbers, which is actually a n minus 1, a n minus 2, blah blah until a 0, and then b n minus 1, b n minus 2 until blah 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 until b 0. What will be the result? How many bits do you require? How many bits do you require to store the result without the loss of the data? So this is n bits. So the result, to avoid the loss of data, we need n plus 1 bits. I will explain this with an example. Okay, so the sum will be Sn minus 1, Sn minus 2, blah 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 until S0. I'll explain this with an example. Okay, let's assume we want to add two 3-bit numbers. How many bits number? 3-bit number. The result will fit into how many bits? 4 bits. Why? Okay, what is the maximum for 3 bits? 2 to the power 3 minus 1, 7. 2 to the power 3 minus 1, 7. 7 multiplied by 7. So 7 plus 7, 14. To represent 14, how many bits are required? To represent 14, how many bits are required? 4 bits. Okay, now this is, okay, now if we add two n-bit numbers, this is 4 bits and this is 4 bits. What is the maximum of 2 to the power 4 minus 1? 15. If we add 15 plus 15, 30. To represent 30, how many bits? 5 bits. Okay, now solve it in another way. Yes, please. So 7 means, okay, 7. 3 bits, the maximum value is 1 1 1. 7, the maximum value is 1 1 1. You add it, 0. 1 1 is 0. This 1 1 1 is 1 and 1 1. 1 1 is 1 1 and 1. How many bits? 4 bits. How many bits? 3 bits. So when you want to perform some kind of a computation, so you will see that what can be the maximum value. What is the maximum value of a 3-bit number? The maximum value of a 3-bit number is 7. The maximum value of a 4-bit number is 15. The maximum value of a 5-bit number is 31. The maximum value of a 6-bit number is 63. The maximum value of 7-bit number is 127. The maximum value of 8-bit number is 255. And then 511, 1023, 2047, 4095, 8191, 16,383, and blah blah blah. Got it? So you can also compute. So whenever you want to perform any computation, so you can say, okay, what can be the maximum value? and that's a maximum value. Got it? Okay, now if you look at here, please think. So now if we are adding to n bit number, so this Sn minus 1, these are all the sum, and this one is the carry out from the last stage. Carry out from the last stage, which is the MSB stage. Got it? Any question? Should we proceed? Okay, now we want to, if we want to multiply two n bit numbers, should I rub this off? Yes. Okay, now if you want to multiply two n bit numbers, so if we want to multiply two n bit numbers, so now this is the multiplication sign and this is an n bit number. So this is an minus 1, an minus 2, blah 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 until a0, and bn minus 1, bn minus 2, blah 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 until b0. How many bits are required to store the result? Think. Why n? We are multiplying. Okay, for a 3-bit number, what is the maximum number? 3-bit number? 7. Okay, so 7. For a 3-bit number, assume n is 3 and 7. 7 multiplied by 7, 49. To represent 49, how many bits are required? 6. 2 to the power 5 is 32. 2 to the power 6 is 64. 49 lies within the range of 32 and thing. So it means, so it means to represent 49, we need how many bits? 6 bits. So actually, if we multiply to n bit number, the result will fit into 2 n bits. So the result will, okay, so we call this as r what? R 2n minus 1, r 2n minus 2 until r0, because this is 2n bits. Okay, now think this is what? Okay, now let's assume if n is 4, what is the maximum value? N is 4, 15. 15 multiplied by 15, 225. And to represent 225, we need 8 bits. So how many bits maximum? 4. And how many bits? 4. And how many bits for 225? 8 bits. Okay, now this is one way to solve. This is one way that how do we calculate it. Now I will explain this with another example that how do we compute it. So should I rub this off? Okay, now I'm rubbing this off, and then I'll say that how can we reach this number. Okay, now I will take with an example of a very small example, and that example is, let's assume we are multiplying two n bit number. This is a3, a2, and a1. Then we b3. Sorry. We want to multiply two numbers, which is a2, a1, and a0, and b2, b1, and b0. What is the size of n? 3. So can we say a0, b0, a1, b0, a2, b0? Then we make a cross. How do we calculate it? A0, b1, a1, a2. So b1, b1, and b1. Got it? Cross and cross. Okay, then we have a0, a1, and a2, and this is b2, and this is b2, and this is b2. Okay, how many bits? 1, then 2, then 3, then 4, then 5. But maybe there are some carry will propagate, and which will go to these 6 bits. Got it? So now this is the way. Now we use different methods. The first method was, okay, what is the maximum number of a particular n bit number? And then we multiply that maximum number with the second maximum number, and that can be the maximum possible value that will come as a result of multiplication. And then we see that how many number of bits are required for that maximum number, and then we calculate it. And now this is the second method. You can also use the same example for a 4-bit number. So then you need how many bits? 4-bit number, how many bits? 8. 5-bit, 10 bits. Same thing. So if we multiply to n bit number, so now this is the simple calculation. You know, this is the first partial product, second partial product, and third partial product, and you can do the repetitive iteration, and then you get the multiplication. So now we are multiplying to n bit number, and the same thing. This is, you know, we want to multiply this with this, and you can calculate it. So what is 1110? 14. 14. 14. 1011. 11. 14 multiplied by 11. So 14 multiplied by 11. 4, 159. Okay, 159, 128, 128 plus 16, 128 plus 16 plus 8, 128.
158, not 159.
This is 140, 154.
Yeah, it should be 158.
Why it should be 158?
Because it's 140 plus 40.
Which one?
Oh, sorry.
154. It is 154. It is 154. So 128 plus 16. 128 plus 16 plus 8 plus 2 plus 8 plus 2. 16 plus 8. 24, 26. 26 plus 128. 154. So the same thing that you do, you can do all these maths and do the multiplication. So if you look at here, now if you look at here, how many bits number? 4 bits. How many bits? 4 bits. The result is 8 bits. So now this is just like an example, and then you can see that how it works. Okay, now these are the tasks. Please go through these tasks. Okay, negative number representation. Okay, now you have studied CMP 120. We can have some positive number and some negative number. How do we define different numbers? Numbers, yes. What are different data types of a number? But if we want to have a positive number and a negative number, how do we define it in CMP 120? Yes, unsigned int. Unsigned int or unsigned short. In unsigned short, if you remember, unsigned short is a 2 byte, and 2 byte will represent some value from minus 32,768 to plus 32,768. But if it is if it's signed, if it is unsigned, it will range from 0 to 65,535. And I will explain the logic behind this. So till now we have considered how unsigned numbers or non-negative numbers can be represented. There are 3 common ways of representing the signed number, which are represent both positive or the negative numbers. But in C++, how do we represent positive numbers? Positive numbers are represented with the unsigned keyword. If you say unsigned short, it is positive. And if you say short, by default, it is signed. Got it? But how do we represent it in digital system design? The first formula is called as the sign and the magnitude formula. So now we have some number, and for that number, we also need to know the size of the number. Okay. So 12. What is the code for 12? 1100. 8 plus 4 is 12. Okay. Now, so we add some another symbol. We call this as S. S means for signed. Okay. And then NS. And then 1100. So it means that if it is 0, 1100, it means it represents what? Plus 12. And if it's 1, 1110, it represents. Got it? So now we have in computer field, we have 2 type of fields. One is the magnitude field. This is called as the magnitude field. And this one is called as the sign field. The magnitude field consists of an n bit. So it is n bit. It can be n bit. What is n here? 4. So actually to represent a negative number, we have this signed bit, 1 signed bit, and then how many magnitude bits? N bits. M bits. So these are the magnitude, and this is actually n bits. Got it? Okay, now we have an 8-bit number. We have an 8-bit number. So now this represents the magnitude, and this represents the sign. Okay, what is the maximum value of a 7-bit number? What is the maximum value? 127. 127. So it can represent any number. It can represent any number from the range of minus 127 to plus 127. Got it? If n is 4-bit number, so it will represent minus 7 to plus 7, because 1 is dedicated for the sign. Got it? Okay, so we go through it. Okay, now, and I will explain this with an example, because this example is, and I will explain it with a small example, and that will be very really helpful for you. Okay. So let's assume we have some data which is actually 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. This is a 3-bit data, and assume these are the magnitude bits, and this is a sign bit. Okay, so now if we have a unsigned representation, now we have unsigned representation. Unsigned, the data is unsigned. So this is 0, 1, 2, 3, 4, 5, 6, 7. For an unsigned representation, the data will represent from the range will be from 0 to +7. But when we have the signed magnitude, so these are the magnitude. This will become what? 0, then 1, then 2, then 3. But now 0, 0, sign is 1. It is actually -0 because sign bit is 1. And then -1, then -2, and simple. So simple. So now the sign bit, if this sign bit is 0, it means it represents a positive number, and if this is 1, it represents a negative number. And that's the reason for the unsigned value, the range is always like from 0 to 7, and here the range is from -3 to +0. And in this case, 0 is represented by 2 codes. Even 100 is also represents 0, and 000 also represents 0. Got it? Any questions? Yes, please.
Where you got the one
Which one?
for the 101 and the unsigned is 5?
0. So it's a magnitude bit. So 01 is 1, and minus comes because of the sign bit. So 10 is what? 2, and since this is 1, got it? So now we have the sign bit and the magnitude bit. So what is the largest positive number? So the largest positive number is +127. Why +127? Because it's 0, and all of these are 1. So all of these are 1, 127, because this is 0, this is +0. This is 1, this is -127. And then it is 0, this is +0. And this is 1, actually these are the magnitude bits. This is -0. Got it? So now you can have the range is from -127 to +127. Okay, now so to negate the number, with the sign magnitude, we just do the invert the sign bit. Okay, so now let's assume this is a positive number. Okay, so now this is a positive number, 0, 0, 0. Positive number or negative number? Positive number. Okay, now okay, let's we have 0, 0, 1. What is this equal to? +1. I want to calculate 1. So what I will do, I will just invert the sign bit. So what is -1? The magnitude will remain the same, but the sign bit is changed from 0 to 1. So actually, so now if you look at here, this one is negative. So -0, 0, 0. This is a positive number. If you want to make it negative, so we invert the sign bit here. And similarly, this is a number, positive number or negative number? No, negative number, because we want to find the invert of this. So we just invert this bit. So now -1, so this becomes. So if we say minus, okay, now we have -1, and we say -1, we invert the sign bit. So now it is 101, so it will become what? 001. Got it? So whenever you are changing a positive number to a negative number, what will you do? Invert the sign bit. It is vice versa. You have a negative number, you want to convert it into positive number. Got it? Should we proceed? Okay. Now there are two other ways of representing sign binary number of. Okay, now this is one representation. The other representation are the ones complement and twos complement. And in this course, we will primarily focus on twos complement. But I'm explaining, or we are explaining this sign in magnitude representation and the ones complement representation for the sake of completeness. For the sake of completeness, there can be different representation of the same data in different formats. Okay, now ones complement. Given a binary number x. Given a binary number x, which color? Which color? Red. Which can be represented as an n-bit number, n, Which color? Blue. And its negative number can be obtained in 1's complement. 1 complement is the representation using, so how can we calculate minus x? So minus x is equal to 2 raised to the power n minus x minus 1. Now, if you want to, okay, now, if you want to calculate minus 12 in 1's complement, what is this? Minus 12. How can we calculate it? What is n? What is n here? 8. N is 8 because we want to represent is in an 8-bit number. So 2 raised to the power 8 minus 12 minus 1. Okay, 2 raised to the power 8. N is 8 here. X is 12 here. And then minus 1, and then we convert it. So this is actually 243, and this is actually the 1's complement. This is the 1's complement of this. So 2 raised to the power 8 is 256 minus 12 minus 1. 256 minus 13 is equal to 243. How do we calculate 243? Yes, please. Which one? 2's complement is just like a name given. 2's complement is a representation of a negative. We can represent a negative number in 2's complement and 1's complement form. Now we are studying which complement? 1's complement. So in 1's complement, what is the formula? Okay, now this will look very difficult for you, but how can we calculate 1's complement? It's very simple. Look at the pattern. This is minus 12. This is 12. How can we get minus 12? Invert all the bits. Can you see here? This is 0, 0. Now you have what? 1, 1. So all these, this is 1, 1. This becomes 0, 0. How can we get 2's complement? Just inverting all the bits. Got it? This is called as 1's complement. Any question? Should we proceed? So the largest positive number. Okay, now please look at here. This table is very important. This table is very important. Now we have the same sign number. So now this is the sign magnitude. Now we have 1's complement. 1's complement. The positive number are same. Positive number are same. What is 1's complement? 0, then 1, then 2, and then 3. Okay. Okay, now how do we get 1's complement? This is plus 0. This is what? Plus 0. 0, 0, 0 is plus 0. How can we get minus 0? All 1's 1, 1, 1 is equal to what? Minus 1. So 1, 1, 1 is equal to what? Minus 1. Now we have 0, 0, 1. 0, 0, 1. This is plus 1. If we want to get 1, 1, 0. So 1, 1, 0 is what? So it is minus 0, sorry. This is minus 0. And this is what? Minus 1. And then what is the code for 1? 0, 0, 1. 0, 0, 1 is what? Plus 1. We want to get minus 1. What should we do? Invert all the bits. 1, 1, 0. It is equal to what? Minus 1. Okay, 1, 1, 0 is minus 1. Okay, 0, 1, 0. What is 0, 1, 0? Plus 2. Want to get minus 2? 1, 0, 1. 1, 0, 1 is minus 2. Okay, 1, 0, 0. Okay, now we have 0, 0, 0, 1, 1. 0, 1 is equal to what? Plus 3. We got 1 minus 3. Okay, now this is very interesting now. This is very interesting. Now you have the same number. You have the same values of a number, but they have a different value and different representations. They have a different value and different representation. What is 0, 0, 0 in unsigned? 0. Okay, now what is 1, 0, 0 in unsigned? 4. What is 1, 0, 0 in sign magnitude? Minus 0. What is 1, 0, 0 in 1's complement? Minus 2. Got it? Okay, so how can we get a 1's complement of a number? How can we get 1's complement of a number? Given any n-bit number. Just invert the bits. Simple. Either invert the bits or use this formula. 2 raised to the power n minus x minus 1. Got it? Now ones complement. Okay, now 14. Can you see here? Should I rub this off? No, I don't want to rub this off. So we have this 14. So I will put it here. I don't. Sorry, I'm just like. So how can we calculate 14? 8 plus 4 plus 2. 8 plus 4 plus 2 is 14. So how can we represent 14 in an 8-bit number? So it is 1, 1, 1, 0, and we want to represent it in an 8-bit number. So this is 0, 0, 0, 0. This is what? Plus 14. I want to calculate minus 14 in ones complement. What should we do? What will be the result? 1, 1, 1, 1, 0, 0, 0, 1. Got it? So this is actually minus 14. So simple. And then you can do all these examples. Okay, now 2's complement. 2's complement is another representation. 2's complement. How can we calculate 2's complement? Minus x is equal to 2 to the power n minus x. 2 to the power n, given a positive number, 2 to the power n minus x. So now minus 12. Can you see here? Minus 12 is equal to 2 to the power 8 minus 12, and then it is 244. In the previous case, it was what? 243. Remember? And now 244. So how can I get a 2's complement? Simple. It was 243. Now it is 244. Just add 1. So how can we get the 2's complement? Add 1. Okay. Now so we have, how can we calculate the 2's complement? Okay, now 0, 0, 0. How can we calculate a 2's complement as 0? We can start from 0. 0, 0, 0. How can we take the 2's complement? First, we need to compute the 1's complement. What is the 1's complement? 1, 1, 1. And then we add 1. 0, 0, 0, 0. And 0 is both. So actually, this is. And this is 1, this is 2, and this is 3, because these are positive number. For positive number, we don't care. Okay. For negative number, for what? For negative number. Okay. How can we get the negative number of 100? So 100. How can now we have 001, 001. Positive or negative? Positive. How can I get 2's complement? First do what? Implement in what? All the bits. 1, 1, 0, and then we add what? 1. What is the result? 1, 1, 1. 1, 1, 1 represent now what? Minus 1. Okay, now we have the other quantity. 0, 1, 0. How can I find the word complement? 1, 0, 1, and then you add what? 1. So this is actually 2, and this one is 1, 1, 0, which is actually minus 2. So this is minus 1, this is minus 2, this is minus 3, and this one is minus 4. Why it is minus 4? What is the code for 4? 100. You in what? 011. You add 1. Is 100. So this is actually. So if you look at here, what is the range of the unsigned number in 3-bit numbers? 0 to 7. What is the range in the sign magnitude? Minus 3 to plus 3. So this is 0 to 7. Here is minus 3 to plus 3. And here what? Minus 3 to plus 3. But in 2's complement we have an addition. It is from where? Minus 4 to plus 3. And when the sign magnitude is 1, in all of the possible cases, when it is 1, it represents a negative number, and when it is 0, it represents a positive number. Got it? In all of the following lectures, we will be only interested in 2's complement. We will not be interested in ones complement or something. How can we calculate? How can we calculate two's complement? Yes, please. In ones, first find the one complement and then you add one. Got it? Okay. Now, so two's complement, invert all of the bits and then add one. Two's complement, invert all of the bits, and invert all of the bits means we are computing the ones complement. So now this is the largest positive number in the two's complement is minus 128 plus 128. Okay. Now, can you see here? Can you see here? And there is a big advantage of the two's complement. In two's complement, there is a big advantage, and how we can then calculate the should I rub this off? Should I rub this off? Okay, now. Now, if you look at here, minus 58. Minus 58. Okay, what is the code for 58? Just look at here. What is 58? So 58 is so okay. Now we have 58. We divide it by 8. I'm converting it into octal. It is 72. Got it? 72 in octal. If I want to convert it into binary, how can we convert it into binary? 2 is what? Yes, please. 0, 1, 0. What is 7? 1, 1, 1. And we need how many bits? How many bits? 8 bits. 0, 0. So this is equal to what? 58. How do we compute 58? What is its weight? 1, 2, 4, 8, 16, 32. 32 plus 16, 48 plus 8, 56 plus 2, 58. We got it? Okay, now this is plus 58. We want to compute, yes please. Which one? Because it is an 8-bit number. How many bits? 1, 2, 3, 4, 5, 6, 7, 8. So we put the 2 zeros because it is an 8-bit number. If we have a 16-bit number, then we can add 8 more zeros. Got it? So now in this case, the number is an 8-bit data. If it is a 16-bit data, so we can then add how many zeros? 10 zeros. 10 zeros, because 6 is the, we computed and 8. Got it? And if it's a 32-bit data, then all the most significant bits are 0. Got it? So now if you see here, because it's an 8-bit data, so this is actually B7, B6, B5, B4, B3, B2, B1, and B0, and we want to compute it in 8-bit data. I hope I answered your question. Yes, good. Okay, now how can we compute the 2's complement? First, take the 1's complement. What's the 1's complement? 1, 1, 0, 0, 0, 1, 1. And then we add what? 1. What will become? 1, 1, 0, 0, 0, 1, 1, 0. Got it? It's the same thing. 1, 1, 0, 0, 1, 1, 0. 1, 1, 0, 0, 1, 1, 0. Got it? Then, okay. Now, how can we compute the negative number for it? So now we have for each bit, we have some weight. So this is 2 to the power 0. So it has a weight of 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6. And if you look at the most significant bit, so the most significant bit weight is minus 2 to the power 7, because it's a negative number. When it's a negative number. So now minus 2 to the power 7, what is, then it is equal to what? Minus 128 plus what? Plus 64, 32, 16, 8. We are not interested because all of these 0. And then plus 4, plus 2. And if you compute it, minus 128 plus 64 is minus 64. Minus 64 minus 4. Minus 60. Minus 60 plus 2. So given an n-bit number. So if we have an n-bit number and we have the 2's complement, how can we convert it into decimal? So how can we compute it in decimal? Yes, please given an n bit number. So given an n bit number, so the weight is actually 2 to the power minus 2 to the power n minus 1, and then 2 to the power n minus 2, then 2 to the power n minus 3, blah 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 until 2 to the power 0. Okay, if it is an unsigned number, if it is an unsigned number, so its weight is what? Plus 2 to the power n minus 1. But if it's a negative number, its weight is minus 2. Got it? And this the most significant bit represent what? The signed bit. Okay, now assume that we have a 3-bit data. So now assume we have a 3-bit data. So it will actually minus 2 to the power 2, and then 2 to the power 1, and that's 2 to the power 0. Its weight is what? 1. What is its weight? 2. What is its weight? Minus 4. Because it's a minus negative number. So its weight is minus 2. Remember, the sum of the MSB, the weight of the MSB is always greater than the sum of the weight of all the LSBs. So if we add this 2 plus 1, what is 2 plus 1? 3. So and what is the weight of the MSB? What is this? Minus 4. So the weight of the MSB bit is always greater than the sum of the weight of all of the weights, the sum of all the weights of what? Of the LSBs. Got it? Should we proceed? And then you can transform, you know, you got. So should I rub this off? Yeah, okay. Now I will explain this with an example. Okay, now if you see here, and the same thing, in the same way. Remember. So now we have the same 3-bit table: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. What is its weight? Minus 4, plus 2, and plus 1. It is 0, 0, 0, 0. Okay, now minus 4 plus 0 plus 0, minus 4. Minus 4 plus 1, minus 3. Minus 4 plus 2, minus 2. Minus 4 plus 2 plus 1. Got it? Got it? And that's the reason that now we are calculating. Sorry, no, this is 0, 1, 2, 3. Sorry, this is 0, 1, 2, 3. 1, 2, 2 plus 1, 3. So this is actually 0 plus 0 plus 0. This is 0 plus 0 plus 1. This is 0 plus 2 plus 0. This is 0 plus 2 plus 1. And what is this? Minus 4 plus 2 plus 1. And these are the weights. And this how do, and why typically I use a small bit number? Because it's very, very easy to compute. And then you can expand the same concept to a larger bit number. Got it? So now we have this concept, and then we can expand this concept. So now if this is minus 9, what is the code for 9? 1001. 100 is what? 1 is what? 8 plus 1. So now if you look at here, this is 8 plus 1. And now because we have a sign magnitude, the sign magnitude is 1. It means negative 9. Okay, now if you want to take the ones complement, so the ones complement, so now this is 9 plus 9. So plus 9's value is 0, 0, 0, 0, 1, 0, 0, 1. If you want to take minus 9, so minus 9, we invert all the bits. What is this? Will become what? 1, 1, 1, 1, 0, 1, 1, 0. This is the ones complement. And what's the twos complement? Add 1. The same thing. Got it? Should we proceed? Now these are the tables. So these are the sign magnitude table. This is the ones complement table. These are twos complement table. And this is okay. Now if you look at here, the most significant bit is 0. All of this represent positive number. And here the most significant bit is 1. All of them. So okay, for the positive number, no problem. All have the same value. But for the negative number, so we have different representation. So now different representation. Minus 1 is 1001 here. It is 1110 and 111 here. So these are different representation of the same data in different format. And I'll explain this with an example. Assume a scenario that we have different color coding. Let's assume we have say red, green, and blue. And we say this is 0, 0, and this is 0, 1, this is 1, 0. Maybe it is your coding. And you say no, this is not my coding. I say, oh, red is 0, 1, this is 1, 1, and this is 1, 0. This is your coding. And you say, no, I want this to be 1, 1, I want this to be 1, 0, and this is 0, 0. This is your coding. So we have the same data. In this coding, what is 0, 0? Right. In this coding, what is 0, 1? Right. In this coding, what is 1, 1? Right. So you can have different coding. So we have the same data but different representation. And the same thing is in CMP 120. So in CMP 120, oh, it's a very important. It also depends on the type of the data, and it's a classical example. If we say, let's assume that if we say that we have the character CH is equal to 65, character CH is equal to 65, and int A is equal to 65, and if we say Cout CH, what will it display? No, it will display A. Because what is the type of CH? Character. And what is the ASCII value? 65. And now if we say Cout A, what will it display? 65. So now we have the same 65 code, but since the notion or the type of the data is different, so we can have the same value but have different representation. We can have the same. Well, what is my height? What is my height? 5.6. Fine, for instance. If I say minus 6.2, it's also true. The same data. Okay, my height is 5.6 with respect to the ground, and my height is minus 6.8 with respect to the ceiling. So it's the same data, but a different representation. Okay, now let's assume this is a glass. If it's half empty, it's half full. Same data, but different representation. So the same thing. So this is in the context of C++. So we have different data types, CH and A, but have different annotations. The same thing. So we have the same annotations. So if we say 1100, so 1100 is so minus 4 is represented by 1100 in Feynman magnitude form, and 1011 is in 1's complement form, and the same value has 1100 in what form? 2's complement form. So whenever we want to solve a problem or thing, so we need to know this. There are two different important things that we need to know. We need to know the size of n. Oh, what is n? N is 8-bit or 16-bit or 32-bit. Okay, and we also need to know what is the range of this. Oh, it also depends on whether it's a sign or whether it is unsigned. Got it? So now we proceed further. So what are the rules? So these are all the rules of the MSB. So if the MSB is 0, it's positive. It's MSB is 1, it's negative. Okay. So now this is the magnitude, and this is the sign form. So now we are only considering the 2's complement, not the 1's complement, not the sign and magnitude. Okay. So now all of this, it is the most significant bit. What is the size of the data? What is the size of data? Go on the top. 8-bit. It's 0. Positive or negative? Positive. From 0 to 127. And then it represents the sign bit. Okay, now if we have minus 5, what is the code for 5? 0, 1, 0, 1. How do we get a 1's complement? In what all of this? How we get 2's complement? Add 1. Got it? The same thing. Minus 3, 4, H. H is in hexadecimal. Minus 3, 0, 0, 1, 1 is 3. 4, 0, 1, 0, 0 is 4. Now we use hexadecimal representation. How do we get 1's complement? In what order? How do we get 2's complement? Add 1. Got it? So now this is a 2's complement. So if the most significant bit is 0, it's positive, and if it's 1, it is negative. Got it? Any question? Should we proceed? And can you see here? Remember, whenever we have any n-bit data, so we have n ones for minus 1. So if you look at here, these are all ones. These are all ones. These are all ones. How do we get? Okay, so 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. It is equal to 127. And its weight is what? Minus 128. So minus 128 plus 1 for 127 is what? Minus 1. Got it? So this is minus 1. And then you can say this is minus 1, and then we put it 0 and blah, blah, blah. Okay, so we proceed further. Okay, now in the previous example, we were having the size of the data was an 8-bit data. And now what is the size of the data? 16-bit data. So now when we have a 16-bit data, when we have a 16-bit data, so actually what is now the MSB? M15. In the previous case, what is the MSB? M7. Okay, so now this is so it is D15 and D14 to D0. So this is the sign bit. Okay, now if you look at here, now this is the MSB. When MSB is 0, positive. When the MSB is 1, negative. So now if you look at here and look at the 1, can you see it? For -1, it's always all ones. In the previous example, for -1, it was all ones. Remember? Okay. Okay, now can you see here? This is the decimal representation, this is the binary representation, and this one is the hexadecimal representation. So you can have different representation, and you already studied these representation. Okay, so okay, now 2's complement addition and subtraction. So what is a 2's complement? What is 2's complement? Should I rub this off? So what is the algorithm for addition for a plus b? Perform binary addition on two numbers. Ignore the carry out of the MSB. Check out the overflow. Can anyone explain it? Perform binary addition on two numbers. These are examples. 3 plus 4. 3 is positive or negative? Now we have 4-bit data. Please remember, now we have 4-bit data. Think this data is 4-bit. 3 is positive or negative? Why it is positive? MSB 0. Second example, -2 and -6. Why it is negative? MSB is 1. Okay, now it is -2. What is -2? So -2 is actually, how can we calculate -2? So this is 0, 0, 1, 0. How can we calculate the 2's complement? In what? What will be this? 1, 1, 0, 1, and then add 1, then 1, 0. Similarly, you can compute it for 6. And then think. Okay, now please look at the color coding. Look at the color coding. What is shown in red and what is shown in green? The carry in is in red. Okay, now this is the carry in for the MSB. MSB means most significant bit. So this is the MSB here, this is the MSB here, and this is the MSB here. So we are interested in two things. We are interested in the carry in of the MSB, and we are interested in the carry out of the MSB. Okay, now just look at the MSB of all these things. Are the carry in and the carry out same or different? Same. Can you see here? Carry in is 0. That's 0. Carry in is 0. Carry is 0. Is there any overflow? Is there any overflow? Overflow when it does not come within the range of the data. So if you say 3 plus 4, it's 7. And what is the code for 7? 0, 1, 1, 1. No overflow. Okay, now you're adding -2 and -6. What is the result? -8. And 1, 0, 0 is actually -8. Okay, how do we do 1, 0, 0? 1, 0, 0, 0. Its weight is 1, its weight is 2, its weight is 4, and its weight is -8. So it's actually -8. No overflow. Got it? Now, if you look at here, -3, -8. What? No, -8 plus 4, -4 plus 1, -3. Code is correct. And here, so actually, if the carry in and carry out of the MSB are same, it means that the result is correct. And this is the 2's complement. So now we have 3, and now this is 2, and it's just like an addition. This is just like an addition. Subtraction is nothing but addition. So if we say A minus B, can we see here? So we can say, if we say A minus B, so can we write it like this? A plus minus B. So we can also write it this A plus got it? So minus B. So whenever we want to compute A minus B, so first we need to take the 2's complement of what? B, and then it is the negative number. Got it? So now if you say, okay, now the first example. So we say and minus A minus B. How can we compute A minus B? Yes, please. Minus A plus what? Minus B. So what do we do? 2's complement of what? A and plus 2's complement of B. If we say minus A plus B, 2's complement of A plus B. Got it? So how do you solve it? So now is there any overflow or no overflow? No overflow. This. Now we get another example. In this slide, if you look at here, please, minus 3 and minus 6. Minus 3 and minus 6. What should be the result? Minus 9. But what's the result now? 7. Now there is an overflow. So when an overflow occurs, when we add, and now this is also an overflow. 5 plus 6, 11. What is the code for 5? 101. What is the code for 110? Okay, now if you look at, please look at this particular example. This is a very classical example. This is a very classical example. And if you look at here, can you see here, if the MSB is 0, what does it imply? It's positive. And if MSB is 0, what does it imply? Positive. And then when you are adding it, what's the problem now? So when we add, overflow occurs when we add to positive number and the result is negative. And how do we calculate it? If the carry in and carry out of the MSB are different, then there is an overflow. If the carry in and carry out of the MSB are different, then there is an overflow. Okay, now I will give it with the classical example of a 3. And then please note it. And then we can go through it and then you will really enjoy it. Okay, so now just for the sake, and if you want to solve all these kind of problem, so then you can reduce the size of the problem and then solve the problem. Okay, now if we say, let's assume given a 3-bit number. Now let's assume that there is a 3-bit number. So now this is a 3-bit number. So 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Got it? Okay, now in 2's complement, you always start 0 1 2 3 plus 3 plus 2 plus 1 plus, and then from the bottom you start from minus 1, minus 2, minus 3 and minus 4. So this is the 2's complement representation. Got it? Okay, now take an example. Take an example. We want to add 2 plus 3. So what is the code for 2? 0 1 0. What is the code for 3? Now 2 plus 3. What is the result? 5. Does it come within the range? Does it come within the range? No, because 5. Do you see 5 here? No. So this is an example of overflow. So now what we are adding? So we are adding two numbers. Which one is positive? And then what's the result? 1. 1 is what? 0. This is 1. And then it becomes what? 1. Okay. Now what is carry in? 1. What is carry out here? No, carry out from here. 0. Are they same or different? Different. When they are different, it means overflow. Got it? With the same example, in the same example. So if we say, okay, now this 0 1 0, if you look at the table, 0 1 0 represent plus 2 and it is plus 3. But if you look at the code, it's 1 0 1 and 1 0 1 actually represent what? Minus 3, which is wrong. So this is an overflow. This is an overflow. So the overflow will occur. What is the rule for overflow? If the carry out and the carry in for the MSB side are different, then there is an overflow. Got it? Okay, now take another example. Take another example. Small example, doesn't matter. So now we say minus 4 and minus 3. What is the code for minus 4? 1 0 0. What is the code for minus 3? 1 0 1. We added 1 0 1 1 0 and then what? 1. Okay, now can you see here? Now there is a carry out. What is carry in? Are they same or different? Different. There is an overflow. You got it? There is an overflow. So they are different, There. Okay. Now, if you look at here, so -4 and minus. So this is -4 and -3. Ideally, what is it should ideally it should be what? -7, but -7 is not within the range. So this is called as out of range. So we can say, and this 001 is actually +1, which is actually wrong. Which is actually wrong. Okay, now take in another example. Take another example. Okay, now, and this is a very classical example. This is a very classical example. So if we say -4, so we are adding two numbers. So we are adding -4. What is the code for -4? 00 -4, and you can try with a lot of combination. Please go through home and try a lot of these combinations, and then you'll learn a lot. You'll learn a lot. So if you say -4, we want to add -4 and then +2. So what is the code? 010. So what's the result? 0 1 1. 110 is what? -2. Correct or incorrect? Correct. -4 + 2 is what? -2. What is carry in? 0. What is carry out? Same or different? Same. Problem? No problem. Problem. So what's the rule? Carry in of what? MSB. If the carry in and carry out of the MSB are same, not a problem. And if they are different, it's a problem. And then again, another example, and this is a very classical example again. So now if you say, so 1 1 1 is what? -1, and then 1 1 0 is what? -2. Add it. 1 0 1 1 1 1 1 and 1. Carry in and carry out are what? Same. What is the result? 101 101 -3. Result is correct or incorrect? Correct. And then we discard the carry. So now that's the advantage of the 2's complement. So basically it gives us an easy way to perform the addition. So if we want to perform an addition, so if we say a plus b, normal, no problem. A minus b, a plus 2's complement of b. Okay, minus a plus b, 2's complement of a plus b, minus a minus b, 2's complement of a plus 2's complement of b. When there will be an overflow, carry in and carry out at the MSB side. So given n number. So if we say, okay, now we are talking in specific example. Now this is an example of 3-bit data or 4-bit data. 3-bit data, and this is an example of 3-bit data or 4-bit data. 4-bit data. So now we want to generalize it. I want to generalize it. So now what is the generalization? So the generalization is this. So please remember. So in this example, so we want to generalize the problem. So we say given an n-bit number, and we want to add a n minus 1 general, a n minus 2 blah 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 until a 0, and then b 0 blah 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 b n minus 2 and b n minus 1. Got it? So okay, now this is actually C in n minus 1. C in n minus 1, and then we can say C out n, because if it is n minus 1, then this is the next step. So now, so we say, so overflow will be equal to, so okay, so we can say overflow will be 1. Overflow will be 1 if C out n is not equal to C in what? So this is a general rule. It's all for today. Thank you very much. I would like you to please come in here and mark your attendance. Thank you very much. I already recorded